with electric power from nearby Lima. Dozens of skilled Peruvian engineers and technicians work on the project. Some are employees of the Instituto Geofísico del Perú. Others are university students from Lima, getting practical experience in electrical engineering. Peruvian and Bureau scientists and engineers work together, assembling and installing the many systems and components. To continue this international cooperation, other Peruvians with potential technical skills are being trained by Bureau engineers. In regular classes conducted in Spanish, they are taught basic electronics and mathematics. Many of these men, being trained as engineering aides and technicians, will work at the observatory, staffing the 3 8-hour shifts for continuous operation, including operation of the observatory's huge transformers seen here. Weighing up to 27 tons and standing 15 feet tall, these transformers deliver 3,750 kilowatts of electrical power to the transmitter system. Now we go to the large room housing the condenser bank. Here, 12-foot-tall banks of capacitors stretch for 60 feet. These Peruvian workers are making a final wiring check on the powerful electrical equipment the observatory will need for probing above the ionosphere. These capacitors form a bank having a capacitance of 1,000 microfarads. This bank can be discharged in a powerful electrical pulse rated up to 20,000 joules. In the amplifier room, these electrical pulses are converted into radio frequency power. Each of the 4 amplifiers used in the transmitter was manufactured in the instrument shops of the Bureau. Each amplifier houses a transmitter tube capable of producing over 1 million watts of radio frequency power. The 4 amplifier system is designed to produce 6 million watts of radio frequency power. This maze of pumps, filters, and piping is the water purification and cooling system. It circulates demineralized water through the amplifier assembly. This dissipates the large amount of heat radiated by the transmitter tubes. Heat exchangers cool the water for recirculation. A network of tunnels runs beneath the building. Blowers circulate cool air throughout the passageways. These tunnels contain over 70 miles of cables and plumbing, interconnecting the transmitter components. Cables and coaxial piping enter the equipment rooms through floor vents. Engineers in the control room direct the transmitter energy into the antenna. Here they are seen monitoring every function of the system's operation. Coaxial aluminum piping, made of irrigation pipe, conducts the transmitted and received radio signals through a spark gap and mixer system. This automatically switches the antenna from transmitting mode to receiving mode in millionths of a second. The energy for the radio signal flows through the coaxial piping in these trenches, continuing to the midpoint of the antenna. Each quarter of the antenna is fed separately. Distribution is made to each module. A modular section comprises 1/64th of the antenna. Each module contains 144 antenna dipoles, or 288 dipoles per module. Open wire lines of 1-inch aluminum tubing connect 2 rows of 12 elements each to the central feed point of the module. Power is distributed to the individual radiating elements. This system of feeding permits unique flexibility in use of the antenna and gives it great sensitivity in receiving very weak signals from great heights above the ionosphere. Even with the antenna only partially completed, Dr. Bowles and his staff were able to initiate scientific observations. Here, Dr. Bowles, working in the screen room, is making measurements of electron densities out to 1,200 kilometers. He is using a 160,000-watt transmitter, representing only a small part of the observatory's ultimate 6 million-watt capability. Radio stars, previously not known to exist, were already being observed, and other findings of great scientific significance were being made before the system was complete. Here is the trace of electron densities in the 1,200-kilometer range that Dr. Bowles has just recorded. As said earlier, scientists believe that free electrons extend to great heights above the Earth's ionosphere. Early measurements at the JICAMARCA Observatory confirmed this belief. Even within the first year of observations, free electrons were detected at well above 5,000 kilometers. Other research will be added. Already, preliminary studies of the planet Venus have been made. Soon it may be possible to detect and measure clouds of solar gas driving toward the Earth, and to study the energy balance between the Earth and upper atmosphere, an important factor in our weather and meteorology. The Instituto Geofísico del Perú and the National Bureau of Standards are partners in what are indeed some of the most exciting radio research experiments of our time, searching for knowledge about the Earth's upper atmosphere, interplanetary space, and the universe, with scatter radar and important new technique for space research from the ground.